All right, let's jump right in. We're going to tackle a classic physics problem, and it's a fantastic way to see one of the most powerful ideas in all of science, the conservation of energy, really do its thing.
So here's the puzzle we're going to solve together. Now, anytime you see a problem that's asking about motion and distance, but it doesn't mention time, that should be a giant flashing light in your brain. It's a huge hint that the best, cleanest way to solve it is by thinking about energy.
Okay, so let's lay out what we're working with. We've got a block, let's say its mass is m. It starts from a height h on a ramp that's totally frictionless, super slippery. Then it hits a rough horizontal surface, and we know the coefficient of kinetic friction for that surface, which we call mu k. The big question is, how far does it go before it grinds to a halt? Now, before we just dive into the math, we need to make sure we have the right tools in our conceptual toolkit. See, solving this is all about how we define our system, and then how we keep track of the energy flowing through it. It's basically a three-step game plan. And the first step is honestly the most important one. You have to choose your system. You have to draw a boundary around what you're analyzing. So for our first try, let's just make our system everything: the block, the earth, and that rough surface.
So what is the energy we're tracking in this system? We call it mechanical energy, and it's really just the sum of two different kinds of energy. You've got kinetic energy, which is the energy of motion, and you've got gravitational potential energy, which is the energy stored up because of the block's height.
Okay, now we need to think about the forces involved, because not all forces are created equal. You have conservative forces, like gravity. They're already baked into our potential energy term. They don't really change the total amount of energy in the system, they just convert it back and forth. But then you have non-conservative forces, like friction. These guys are different. They actually take energy out of our system, usually by turning it into heat.
And this right here, this is the master rule that ties everything together. It's called the work-energy theorem, and it basically says that if a non-conservative force does work, the total mechanical energy of your system has to change. In our problem, the only force like that doing any work is good old friction.
All right, enough theory. Let's get our hands dirty and actually apply this theorem to our sliding block and find that stopping distance d.
So here's the big idea boiled down. The total change in the block's mechanical energy, from the second it's released to the second it stops, has to be exactly equal to the work done by friction. All that energy has to go somewhere, and friction is where it's going. So let's blow this equation up a bit. The change in energy is just the final energy, that's kinetic plus potential, minus the initial energy. And the work done by friction, that's just the friction force times the distance, d. And we put a negative sign on it because friction is always fighting against the motion. And now for the really satisfying part. Let's start knocking these terms down, one by one. First up, the final kinetic energy. Well, the block comes to a stop, right? So its final velocity is 0, which means its final kinetic energy is also 0. Boom, gone.
What about its final potential energy? Well, this is where we get to be clever. We can just define the ground level as our 0 point for height. Since the block ends up there, its final potential energy is, you guessed it, 0. Another one down.
And let's go all the way back to the start. The problem says the block was released from rest. That means its starting velocity was 0, so its initial kinetic energy is also 0. Easy peasy.
And just look at that. That big, messy equation just melts away. All we're left with is the negative of our initial potential energy, which is mgh on the left. All that energy it started with was completely wiped out by the work done by friction. And we know the formula for the friction force is just mu k times the normal force. On a flat surface, the normal force is just the block's weight, mg, so we can substitute that right in.
So we just cancel out the mass, m, and gravity, g, from both sides, and we're left with this. I mean, how clean is that? The distance the block slides is simply its starting height divided by the coefficient of friction. Incredibly elegant.
But wait, we're not done yet. In physics, just getting an answer isn't the whole game. You always have to do what's called a sense check. You got to step back and ask yourself, does this formula actually make sense in the real world?
So first question for our sense check, what if we start the block from way higher up? Your gut feeling probably tells you it should slide farther, right? And yup, our formula totally backs this up. D is directly proportional to h. If you double the starting height, you're going to double the sliding distance. The math matches our intuition. Perfect.
Okay, next test. What if we make the surface rougher? What if we crank up that coefficient of friction, mu k?
And again, the formula works like a charm. D is inversely proportional to mu k. So a rougher surface means a bigger friction force, and that's going to bring the block to a stop a lot sooner. It just makes sense, right?
And this is where it gets really cool, when we push our formula to the absolute extremes. What if the height is 0? Well, the distance is 0. It doesn't move. Makes sense. What if there's no friction? Well, our formula says the distance is infinite. The block would just slide forever. And what if friction was somehow infinite? It would stop instantly. Our formula holds up in every single crazy scenario we can throw at it.
Now, just to make sure this concept is totally locked in, let's rewind and try this a different way. Let's go back to that very first crucial step and change our choice of system. So what if, this time, we define our system as only the block? Nothing else? Well, if the Earth isn't in our system, then suddenly, potential energy isn't a thing anymore. Instead, gravity becomes an outside force that does positive work on the block as it slides down the ramp. The work-energy equation looks a little different, but, and this is the magic part, when you work through all the math, you get the exact same answer for D.
So what's the big takeaway here? It's that the physics always works. The right answer is always the same. But how you frame the problem, how you choose your system, that can be the difference between a total headache and a really elegant solution. And, that's an insight that's useful pretty much everywhere, not just in a physics class.